Hi, everybody. It's Mrs. Pendleton. I braved the world to come to my classroom and try to give you a lesson for this week. And I want to start out with a very simple demonstration. All right, I've got a book of matches. And what we're talking about today is potential energy diagrams. The chemicals in the match, they represent potential energy. The chemicals, once you get them started, they have energy and they'll just go on their own. Spontaneously, it'll combust into fire. But there's a couple of things that you need to have in order for this to work. The collision theory says the molecules have to come together with enough energy and force to be able to react. All right, so here I'm going to go and show you. All right. I guess that wasn't enough energy. Okay, maybe I need to press harder. No, that didn't work. All right, so third time's a charm. We're going to get that match lit. And there we go. It's a spontaneous reaction at this point. Okay, so on this graph, I'm going to explain the parts of it real fast. The dependent variable on the y-axis is the energy. The independent variable is the reaction rate. This part right here is the potential energy of the reactants before they get to react. This here is the potential energy of the products. This is the energy that they have after the reaction. This is called the potential energy of the activated complex. It's the whole thing. The difference between the energy of the reactants and the products, that's your delta H. That's the amount of heat that's either absorbed or released. The top part is called the activated complex. This is where the reaction has enough energy for the molecules to spontaneously go to completion. All right? Now, the way the graph is drawn, the reactants have more energy than the products. So where did the energy go? Well, this is an exothermic reaction, and it's going to be released. The energy will be released to the system or the environment. In the second graph, it's set up exactly the same way, except you can see the shape of the graph is different. Here, the potential energy of the reactants is less than the potential energy of the products. So the change in heat is also delta H, but in this case, it's endothermic. Energy had to come into the system in order for that reaction to happen. Now, two other things I want you guys to take a look at. This line right here is still the activated complex, but it's with a catalyst. It takes a little less energy for those molecules to get to the potential activated complex and make it to completion. If you draw the line a little bit higher, this would take longer. It's like trying to climb over a taller mountain. So this is the activated complex or the activation energy with an inhibitor. Catalysts speed up a reaction, inhibitors slow it down. I've given you a lot of information on today's lessons, so I'm going to make this really short. And I'm glad I got a chance to come in today. See you later.